So thank you very much for inviting me. I'm very happy to see some old acquaintances and familiar names in the participant list, and indeed greetings to you all. I hope you are all well. I'm so happy, and I'm also honored to be here as a keynote speaker and participant to this online symposium. First, just for those of you who don't know me, a few words about myself. Yes, as you can see, it is a bit freezing here, so we have to dress properly. My background is in environmental engineering and environmental sciences, and I have been working for almost 30 years in material and nutrient recycling, closing nutrient loops, circular economy, which is the word of the day, making circularity a business, and also sustainable development. Starting from this year, I have changed my position from researcher and a lecturer to an impact leader, 1 out of 3. And my task in our university at the moment is to promote our impact in terms of research concerning sustainability themes like ecological innovations and sociocultural challenges. And still, I would say that sanitation issues are very close to my heart. So I'm happy that I had this chance to come and speak to you. And indeed, these are my tasks at the moment. But if we go to the theme of the day, a little bit of background, issues like Professor Matsui also was presenting. Briefly said, and in Scandinavian style, straightforward, say we have an issue. We have a big issue in terms of biodiversity degradation, and also restricted fossil and mineral resources that we have, especially in terms of phosphorus, as we heard before, but also nitrogen. We have enormous amount of nitrogen in the atmosphere. However, binding nitrogen to a fertilizer is highly energy intensive. We use a lot of energy, and that's also a fossil energy to bind nitrogen to a fertilizer from the atmosphere. And yet at the end of the cycle, at best, if, for example, the urban wastewaters are treated and managed in the wastewater treatment plant, what happens to the nitrogen? It's actually bubbled back to the atmosphere. So it's wasted in that respect. So at the moment, in wastewater treatment, we don't talk about nutrient recovery. We talk about nutrient removal. So it's not getting back to the water bodies, but it's removed. But again, utilizing these nutrients are not considered. So this is one very important issue to consider in terms of nutrient reuse and recycling, and also the theme of this talk, which is urine. Secondly, we have also limits. Now, I refer to very, very old publication from 1972, assuming that there are quite many students present here. This might be something that you don't know about, but in 1972, a book was published called The Limits to Growth. Now, the issues or the facts are in this book. We have to remember that they reflect the time in 70s. So like the years and the amounts of resources we have are based on the knowledge we had at the time. And we have to, so these like predictions that within the next 100 years something will happen are not necessarily absolute and final, because things have changed. We are now much more efficient, and there are new resources found. However, it points out the very important issue, like it was in the previous slide as well. We have limits, and we have to live within these limits. And that's why reuse, recycling, and recovery are important issues in terms of nutrient reuse as well. So we need to go circular. We need to get circular. And for example, these days, a term called circular economy has been launched. One need to remember that there is always the economical side included when we talk about circular economy. But from linear to circular, that is the main point I want to emphasize to everyone. Whether we talk about urine, whether we talk about bio-waste management or some other material or product, things need to cycle and the economy needs to be built around it. Even in scientific research, which is highly valued, very important, eventually it should lead to something beneficial from the economy and from the people point of view, as sanitation is a basic need that needs to be filled in a sustainable way. Okay, so this was the introduction. And now I would like to go to the first part, urine, the potential that urine has as a fertilizer. Most likely, these things that I'm going to show are very familiar to most of you. However, this is just a one, or these are just like our examples, another amendment, another addition to the very same theme that many of you have studied already, urine as a fertilizer. These pictures and this information I'm about to present you are from our experiments we had been doing. We started about 5 years ago, and this project ended a couple of years ago. Source separated urine as a fertilizer. But why this was important in Finnish context? It was because it was the first field scale experiment or field scale experiments that were done in Finland. We did use, it was a tractor scale, it was a real scale, and we did these experiments together with farmers around this Tampere region. And it was a big issue here. It actually attracted a lot of media. So back 3-4 years ago, we were really famous. This was interesting to people. It was also a bit laughed at. You all know that, because using urine as a fertilizer, it's intriguing, it's exciting, but at the same time, people are very curious and a little bit afraid of as well. But we got this attention. We also did spread the urine to the field manually as well, because in some fields the plots were pretty small. But nevertheless, the point was here that the conditions were real, and we were working together with farmers who were interested in this matter. We had 2 farms in collaboration with us. And here you can see some of the facts of the characteristics and quality of the urine we were using. The main interest and what we actually used to calculate the fertilizer need was nitrogen. So you can see here the total nitrogen amount. That was 2,800 milligrams per liter, 2.8 grams per liter. It's quite dilute, actually, and the reason for that is that it was collected from Hiedanranta. Those of you who have been in the dry toilet conferences here in Tampere a couple of years back, it was organized in this environment in the Hiedanranta area in the city of Tampere. And there are these dry toilets, which are located in a place that was used to organize events. concerts, music events, seminars, and so on. So it's quite understandable that in this respect, the urine is quite diluted. But we did measure also the other elements, but what we used mainly was this total nitrogen, phosphorus, and potassium to calculate how much urine we needed to these fields. Another thing that we measured was E. coli and Salmonella. Why only these? Because in Finland we have this, and here we come to the regulations and legislation. We have legislation concerning organic fertilizer products, and they define the limit values, first of all, to metals, heavy metals, also certain range to where the nutrient content should be. So that defines on what you can call the product, and whether it is liquid or solid, whether it is a compost or something else. There is quite a list of different categories where these fertilizer products are categorized. But from microbiological point of view, no organic fertilizer product is allowed to contain plant pathogens. E. coli amount should be less than 100 colony forming units per gram, and there should be no salmonella. These are the standards in Finland. So this is what we did. This is what we analyzed. And based on these standards, this urine was perfectly safe. Before getting into the into the other matters, also in terms of heavy metals, because we don't have these anymore in our diet, and heavy metals in the environment, there is no longer lead in the fuel, so we are no longer exposed to heavy metals. So, and everything we are exposed to, we excrete in urine, and as a result, the amounts of heavy metals in urine and also fecal matter are quite low, practically insignificant. So these do not add any heavy metal load to the environment. Now, a question asked always here, if you talk about sewage sludge, urine, or fecal matter as a fertilizer, is what about the micropollutants? It is a big concern because people are aware, and we know we are surrounded by chemicals. Chemicals are everywhere. And furthermore, we use these days more and more pharmaceuticals. We need medicine. So what we did, we analyzed pharmaceuticals, and we analyzed more than 55 different pharmaceuticals and hormones at the time, and this is what we found. The main thing what we found was, sorry, there's a typing error, but the main thing what we found were painkillers, anti-inflammatory painkillers, caffeine, and some other very, very common pharmaceuticals that we need, like beta blockers for heart condition, some corticosteroids, hydrocortisone is needed to use, for example, asthma medicine, and some antibiotics. This is what we found. And for example, if we would do the same in Central Europe, the amount of antibiotics would be much, much higher, because in Finland, the use of antibiotics is quite low, or moderate. Antibiotics are used only if they are needed, not just in case, only if they are needed. So these are the number of the pharmaceuticals we found in the urine used. And we also analyzed some other organic micropollutants, total of 339 of them. And this is what we found. We found mainly different phenolic compounds and some phthalates. Phthalates are basically understandable to find. Of course, we do use a lot of plastics. We do use a lot of plastic cutlery, for example, everything is packed in plastics, and furthermure, we had no option but to store this urine in plastic containers. So it's very well possible that there is some phthalates dissolved into the urine. And phenols are something that occur also in urine naturally. So that is not a surprise that there is also phenols there. Actually, urine contains over 3,000 different organic compounds naturally, and phenols are one of the most common ones. Of course, we are exposed to these as well. If we smoke, we have phenols in urine and phenolic compounds in urine. And also some triclosan was found. And here you can see the actually the field and the fertilizer level that was used in 2017 and 2018 in these fields. So all in all, this is a summary table. This is the number of analyzed organic micropollutants we analyzed from the samples. From urine, we found a total of 30 different, so 239 different compounds were analyzed. We found 30 from urine. We found none from the soil at the end of the growing season. And from the grain, the experiment plant was barley. So from the grain, we found none except progesterone. A female hormone was found from the grain, and this was really surprising, but after studying literature, we discovered that progesterone is something that plants can produce also naturally. So most likely the existence of progesterone in the grain was due to that, not because of the urine amendment, because the amount was so low in urine, and furthermore, we didn't find any in the soil. It was all degraded. So all in all, soil has, as in the previous keynote speech, it was pointed out, soil contains a lot of microbes, a lot of bacteria that are able to degrade these micropollutants. And from pharmaceuticals, many of them actually are also quite easily degradable. Some of them are not. But then again, fortunately, the amount of these compounds in urine are quite low. Okay, the results in terms of yield were very, very promising. Here in the, you can see the two fields, two different fertilizer levels, which also were quite low. And this is the barley variety, Harbinger and Volmari. From 2 or 3 different summers that we were doing these tests, you can see that urine used as a fertilizer produced at least equally good yield compared to mineral fertilizer. The difference here between these different years, 2016, 17, and 18, is explained with weather conditions. Firstly, in 2016, I would say in Finnish context, the summer weather was more or less normal in terms of rainfall and temperature. 2017, it was really, really wet. It was raining the whole summer, which caused reduction in yield significantly. And in 2018, we were facing drought. It was really dry. So in that respect, I would say at least in 2018, the weather conditions overruled the effect of the fertilizer. So dry conditions caused these issues. But what is the most important message here is that urine showed at least equally good or even better for, yield results compared to mineral fertilizer, and that's enough. If it is at least equally good, that is enough to show the effect of urine as a fertilizer. Here are 2 pictures. Since we are not live, we are online, I just show these to you now, and ask you to guess where in these fields the urine amendment was done. In what part of these fields the urine amendment was done compared to mineral fertilizer. I bet you cannot guess it based on how it looks like from the above. But these are the parts where the urine was used as a fertilizer. You can't distinguish that based on how it looks like and reflected to the results we had. Then we also examined the soil quality. One concern in urine is the amount of salts. There is a lot of sulfate, chloride, nitrate, also sodium. We didn't find any accumulation in the soil. Well, if we have the rainfalls as we did, it's no wonder. We didn't find any acidification effects, but instead, as said earlier, weather conditions did have a significant effect on growth. And we didn't find any pharmaceutical accumulation or organic compound accumulation in soil or barley grain. So it works. This is the main message, and I know that many of you know that already, but it does work. Secondly, the part of this speech is about making urine a product, make it something that has value. That is an issue. What is quite obvious that unless the source separation or the urine use are located close to each other, it is no use to transport urine or any other manure or compost for that matter very long distances. In Finland, it has been estimated that 20 kilometers is the maximum. And in terms of city areas, it's quite impossible to meet these limits. And in that respect, for example, the school projects that were presented and exist in many parts of the world, if the school can use, for example, the urine and the fecal matter in the garden or in the vicinity, then it's worthwhile. But if we talk of big scale source separation, then it would be better if we can treat the urine somehow on site and then transport the product, which has more value to somewhere else. And this is the theme of this part. So this is sort of the traditional sanitation value chain. I call it business as usual. This is not that usual, I know that, but basically it starts from the capture, containment or separation, emptying, transporting, treating, and safe reuse or disposal. And one thing I would like to sort of give to you a food for thought. I have started to dislike the terms disposal, waste, and wastewater, because in my opinion, we shouldn't dispose anything. We should always consider it as a resource which can be reused. Waste has a negative sound. It's something unwanted, while in this respect, this should be something very, very much wanted and needed, and same applies with wastewater. And if you know any professionals in linguistics or language professionals, what I throw you a challenge. Please invent a term that would replace waste and wastewater to something positive that can be reused. I think it's our duty to do this. And I have already invented a term in Finnish language, but it's impossible to translate it in English. But this is an idea. How about if we do it in a different way and turn this whole philosophy the other way around? So basically turn it, first of all, we should go circular and increase value to the urine so that it's worthwhile use it as a fertilizer and make it a business. That's what circular economy is all about, so that it is worthwhile either that you can sell it, it brings income, or it saves money on some other part of this chain or circle. This is a very important thing to remember. In the modern wastewater treatment plant, this is a process of wastewater treatment plant in Amsterdam, and it comes from the publication of Van der Hoek. There is a reference at the end of this presentation. If you look at the flows, the wastewater flows in this particular wastewater treatment plant, but I would say that the ratios are the same in every one of them. It's so small amount. This is 0.36 cubic meters times this is the unit. Sorry, this is the unit. 10 power 6 cubic meters annually. So this thin yellow line here represents urine of all the volume of water, incoming water to the wastewater treatment plant. So you don't, and this is the total amount, 63.6. And out of that, 3.36 is urine. But out of all the nitrogen that enters the wastewater treatment plant, this is the amount that is in the urine. So vast amount of nitrogen is in the smallest fraction of incoming water. So wouldn't it be worthwhile separating in terms of nutrient recovery? The same applies with phosphorus as well. So of course, from the gray water, some phosphorus is flowing in, but the ratio is pretty much the same. That majority of phosphorus is also in urine in incoming wastewater to the wastewater treatment plant. So what we have done actually in this very same research where we used urine as a fertilizer, we did life cycle analysis and environmental impact analysis. This was done by our partner, Finnish Environment Institute. So we compared the environmental impacts of source separating sanitation systems in 20 years of life cycle. We compared climate change, freshwater eutrophication and acidification effects. And of course, a lot of assumptions needed to be made. We calculated the wastewater treatment. It was made for a household of 3 persons with 85% annual use. And the scenarios are presented in a while. This is the average amount of nutrients produced by 1 person per year in Finnish context with our diets, and these are the numbers which are used also in dimensioning the wastewater treatment systems on site in rural areas. You can see also, of course, the obvious that most of the nitrogen and phosphorus are in urine. And these are the basic assumptions, what kind of pipelines, what kind of tanks, and so on. I'll skip these and get to the different environmental impact alternatives. The first alternative, and this concerns rural areas, not urban areas which are connected to sewer system. This is rural areas. Typically in Finland, in households, we have 3-chamber septic tank, 2 or 3, where the wastewater is settled, and then the sludge is emptied once or twice a year and transported to the wastewater treatment plant, digested, composted, and so on, and used as a fertilizer, except when it's not used as a fertilizer. And this is an issue I asked a question previously from Professor Matsui about this acceptance of the use of sludge-based fertilizers. So it is allowed, it is regulated here in Finland as well. But for example, our food industry, especially the organizations which are controlling the grain industry, like breweries and bakeries that are using grains, they have informed the farmers that they have made contracts with that they do not accept grains that are grown using sewage sludge-based fertilizers. So by law, it's allowed, but the industry is not going to buy it if they use sewage sludge. So the farmers don't use it because otherwise they can't sell their products, which results in a problem where to put all the compost, for example, that has been made from sewage sludge, treated sewage sludge. And there is a contradiction, obviously. It leads to the situation where the sewage sludge is actually used in landscaping, which in my opinion is the same as burying into the ground. Landscaping means, for example, roadsides, parks. It's not nutrient reuse. It's burying the stuff underground, where it's actually a time bomb. Imagine all the amount of phosphorus that is in the precipitate from the wastewater treatment plants. It is clearly creating an effect. Okay, these were compared to separating system, urine separating system, or black water separating system, where gray and black water were separated. And then a life cycle analysis was done. I see that the time is flying, so I'll go faster a little bit. What we found actually is that urine separation, which is the yellow bar here, clearly brings, or black water separation for that matter, separation in any case, clearly brings beneficial effects in terms of eutrophication. That makes sense a lot. To acidification, urine separation poses a little bit of risk, but this is not a major risk compared to business as usual. So all in all, in terms of eutrophication especially, which is of concern, the nutrients are in the wrong place. The separation is definitely beneficial. What comes to the paths of nutrients, basically you can say that the more green there is, the better. So in terms of nutrient potential, urine separation and black water separation are beneficial. This is the urban reference, meaning the centralized systems in urban areas. There is a nutrient potential, of course, with these restrictions of the sludge use. But basically, nutrient recovery potential is clearly higher in separating systems, while the emissions to water and soil, of course, are clearly diminished, reduced. And compared to the present wastewater system, these different alternative scenarios, of course, urine contains a lot of phosphorus and nitrogen, so separating that enables the nutrient recovery much better. And in overall environmental impacts of these alternative systems, the white dots here and here indicate the net environmental impacts. Clearly, the urine separation is beneficial in terms of eutrophication. With acidification, you can see the scale. The bar looks a little bit big, but if you look at the scale, it is greater, but from taking into account the overall benefits, it's not that significant. And in terms of climate change, again, urine separation is clearly much more beneficial. So it enables greater nutrient recovery rate compared to conventional wastewater treatment if we separate the urine. Environmental impacts are lower, but of course, separating systems are much more expensive compared to the conventional ones because they need investments. We don't have separating pipelines. However, another point of view here is that, for example, in Finland, we have a lot of old sewer systems that need to be prepared. So if they would be planned so that separation is possible and we could collect urine, for example, to the wastewater treatment plants in urban areas, in time that would pay back. But again, here we run into people's minds. The first option is that it's impossible, it costs so much. But I would say in terms of environment, the current system also is quite costly. So for the environment's sake, it's beneficial to separate and reuse, definitely. What are the options then to manage? I'm checking the clock. Okay. Nowadays, I know that my Japanese colleagues are also doing this research in treating urine so that it aims at decreasing the volume, maximizing nutrient recovery, managing pathogens, micropollutants and salts, and then enabling nutrient reuse without biases or environmental health risks. Do I have much time, Nenny? Can
yes,
you please?
still, yes, 3 minutes
Okay.
more.
Sorry? How many?
3 minutes, can you?
3 minutes, okay, yep. I will skip some of them. This is just to show different kinds of means to treat urine to make it a fertilizer product. And this is important part in the value chain. This is the part where the value is increased. I have quite a lot of presentations about different technologies, and this Hiedaranta, which some of you know, you have been there, about different technologies. One of which I would like to especially mention is this alkaline dehydration, which is invented by our Swedish colleagues in the Swedish Agricultural University. This is what we tested. And all in all, my opinion is that the more simple, the better. The more complicated the treatment method is, the more vulnerable it is, the more expensive it is. Please check the reference here about alkaline dehydration. It's very simple. It does require some energy for evaporation, but it recovers most of the nutrients, and this is what we have tested. These are just examples of our test environment in the basement of Hiedaranta Manor. These are the results. We got pretty good recovery. Also meeting, here you can see the Ministry of Agriculture and Forestry legislation in terms of heavy metals, except for cadmium, which exists in ash. The material where the urine is led to is ash and lime. Ash contains cadmium, so it might increase the amount of cadmium in the end product, but this can be dealt with. So these are the examples we've done in terms of also pharmaceuticals were analyzed, and the results were pretty much the same as in the previous ones. We also tested this so-called NP harvest process. We have the similar ones. So, excuse me, the point is that there are methods, there are different technologies to treat urine so that the nutrients can be recovered. And nutrient is nutrient. It doesn't matter where it originates. If you get the nutrients, you can reuse them. I'll show you here some pictures of the examples we have done in concentrating urine using ultrafiltration and reverse osmosis, and with the results we have got. So there are means to manage urine for fertilizer, and the more simple it is, the better it is. And with these words, I would like to thank you. This picture is the apparently the last known carriage to take night soil out of Turku, one of the oldest cities in Finland. It's in the museum these days. So thank you very much for your attention. And sorry for the rush at the end, but this is how it is when you have a lot to say. And here are also the literature.